You look at the course of the last 15 years, the technology has advanced tremendously, but yet you stand back and it still looks largely like a cartoon. And the reason for that is because there are three things that are kind of largely missing. There are three things that are largely missing. Reflections aren't right. Shadows aren't right. And refractions are really, really hard to do. These three lighting effects are really hard to do in rasterization. And yet we apply all kinds of amazing tricks to work around them, but it's just really, really hard to simulate the effects of light by starting from a geometry, because you have to start from the light. And that's where ray tracing comes in. About 30 years ago, one of our researchers, Turner Whitted, invented a technology, wrote a paper on iterative ray tracing, and it's taken over 3 decades for the entire industry working together to try to find a way to do it in real time. Tracing a light from your eyes into the world, from your eyes because it's the most clever and the most energy efficient way of doing it, instead of from the light. You trace it from your eyes, only the things that you see. Where it intersects a triangle or an object, it would then follow to the next point of light, whether it's reflected from another object or from a light source. And every single time light touches that geometry, it would affect the color of the pixel or the lighting of the pixel that comes to your eyes. One ray at a time, we would trace it into the world. And just by doing that, which is basically simulating the laws of physics, the way that light works, and if we capture the materials, we capture the light transport behavior of the medium, we capture the geometry, and if we could do this fast enough, shadows just appear, just like it does in the real world. Lighting just works. Reflection just works. Materials look rich. It just works. No light baking is necessary. No faking is necessary. It just works. That's the beauty of ray tracing. However, the computational requirement is just daunting. And it's taken us 3 decades to get here. And let me show you some of the inventions that we think will be necessary to take it to the next level. And so if you take a look at the top, reflections on ray tracing. RTX on, notice everything is reflected as you would expect. The Rubik's Cube reflecting on the ground in the mirror. Okay, so reflections, RTX on, notice everything just works nicely. In the case of rasterization, it uses this thing called a screen space reflection. So it basically takes what is drawn into the screen, into the frame buffer, as the reflection map. And if you can see it on the screen, then it could use it as a reflection. Unfortunately, the things in the back of that Rubik's Cube, it can't see. And therefore, as a result, it can't be used for screen space reflection. And so the back of the Rubik's Cube, which is being reflected into the mirror, because the mirror can't see the back of, using rasterization, can't see the back of the Rubik's Cube, it can't use it for a reflection map. The same thing in that little tiny shelf on that mirror. If I were to turn off RTX off, you would notice that it's broken. Another thing that ray tracing solves is shadows. This right here is called the umbra. Umbra is a Latin word for the eclipse, otherwise known as the shadow. In the case of rasterization, it simulates a shadow by essentially drawing the projection of the shadow on the ground into a geometry. And it does it by using a point light. In the case of area light, some of that light goes to this side, some of that light comes to this side, and as a result, the umbra and the penumbra, the partially occluded parts of the shadow, are not crisp and clear. I wish this would go over again so I can show you. As a result of using ray tracing, we can now have soft shadows. Global illumination. Global illumination is necessary when you don't pre-bake the lights. If you pre-bake the lights, if the world changes on you in the video game, all of a sudden your pre-baked lights don't work. And so notice, this is RTX off, and when the building falls apart, the lighting is just wrong. RTX on, when the building falls apart, it still works. Okay? And of course, image processing. Artificial intelligence has the ability to learn what is the right image to synthesize. And maybe as a result of that, we could use lower resolution textures, less amounts of textures, and use artificial intelligence to synthesize the virtual world because, quite frankly, it's natural anyways. And so AI could use it to synthesize higher resolution images. AI could use it to synthesize textures and synthesize all kinds of interesting geometries that we can explore within. AI and ray tracing are two fundamental pieces of technology that we believe will define the next generation of computer graphics. So we invented a new computer graphics technology to enable the next generation of graphics. We call it RTX, the NVIDIA RTX. In order to enable the next generation of computer graphics, in addition to rasterization and compute shaders, we had to add two new ways of computing. One is ray tracing, the ability to trace a ray through a complex world and do it as fast as possible. And then number two, artificial intelligence. Artificial intelligence for the synthesis of worlds, synthesis of images, synthesis of animation. These four key technologies are going to form the foundation of the future of computer graphics. New GPU, Turing. The Turing architecture basically consists of four things. The first thing, of course, is the GPU itself, the Turing GPU. The second is a brand new shader architecture. We added a brand new engine called Tensor Cores. Tensor Cores has the ability to operate on the deep learning network's fundamental operation of linear algebra, A times B plus C, 4x4 linear matrix, linear algebra matrices at the speed of light. And then lastly, in order to do ray tracing, we have a dedicated functionality called the RT core, the ray tracing core, that basically flies through this data structure called the bounding volume hierarchy, which describes the geometric world and deals with all of the intersections of which triangle is hit by the ray and what other rays are spawned from it. That is called the RT core. These four characteristics describe the Turing architecture. The performance, the throughput is incredible compared to Pascal. Pascal starts out with the largest version of it, which is now in the Titan XP, and Turing starts out with the largest version of it, which is in the Titan RTX, what some people call T-Rex. These two largest chips is what the entire family of Turing and Pascal are derived from. In the case of Pascal, the largest chip is 11.8 billion transistors, almost 500 millimeters squared, has an I/O of 11 gigabits per second using the fastest memory at its time called G5X. In the case of Turing, 18.6 billion transistors, 754 millimeters squared, and 14 gigabit per second, the fastest memory you can use today, called the G6. These two dies is what the entire family is derived from. And if you take a look at these two dies and their computational throughput, you can think of it this way. Here we go. The compute shaders of Pascal is 12 teraflops. In the case of Turing, it's 16 plus 16. 16 teraflops, trillion floating point operations per second, and 16 trillion integer operations per second. The shared memory and the register files is 12 megabytes large. In the case of Turing, 25 megabytes. In the case of L2, 3 megabytes to 6 megabytes. Basically, Turing has twice the basic throughput of computational compute horsepower. And if you then add on top of it the two new processor cores for tensor processing and ray tracing, you get, in the case of Turing, 130 trillion operations per second and 11 gigaarrays per second. Now, it's possible for us to use Pascal to do both of those things. And the reason for that is because Pascal is a general purpose compute program accelerator. And so it could run tensor operations, just about 1/13 the performance, about 1/10 the performance. In the case of ray tracing, it could also run ray tracing. However, it would have to run it at about 1/10 the performance. You take all of this computational capability and you put it inside this compute framework we call RTX, and on top of the driver called DXR, accelerating driver called DXR, and then integrating it into the Unreal Engine, we can then apply that to do amazing things. This is what I'm going to show you is a demo we've shown you before, except we've made some refinements, if you will. So let's enjoy this.